Hello, welcome to Chapter 8 for Physics Without Calculus for Aquinas University. This is the OpenStax textbook and OpenStax PowerPoint, the ones provided by the publisher. I will be going over linear momentum and collisions. This is a rather straightforward chapter, similar to Chapter 7, where it's just wrote applications of Newton's laws of motion. So I'm not going to go super in depth in the conversations. It's just find the equation, plug in the other information, more or less. But we're starting to go over the concepts also. Likewise, I'm going to try to go over the real world implications of everything here. This is day-to-day life, essentially, right? Again, just like Chapter 7, this is the functions of every single thing you do. But let me explain the Greek letters behind it in the equations, essentially. So, what do I mean when I talk about momentum and linear? Oh, sorry, I also forgot to say, I'm going to be going through the slideshow, referencing the text. I'll be going through selected questions in the textbook, not all of them. Pause the video anytime you want. This is not meant to be your sole source of information on this subject. Cool. So, what is momentum? Well, here we have a picture of some rugby players rugbying it up. And the way contact sports like rugby or American football, hockey, all these things work is essentially a lot of collisions, and collisions are a key factor, a key way of understanding physics. Collisions are at a super scientific level. Some of the most expensive experiments we do on this planet are at CERN, at the Large Hadron Collider in Europe, and they're basically watching particles collide into each other, essentially, right? So what these big burly men here are doing in this image is a large scale version of the equations we'll be talking about. So in particular, this is a conversation on momentum. What is momentum? Well, this P here is the excuse me, is the letter we use to describe momentum. In other words, it's a bolded P, so momentum is a vector, and momentum is simply defined by how big you are and where you're moving, your mass and your velocity. Multiply your mass times your velocity, you have your momentum. The larger the thing is, the more momentum it has. The faster it's moving, the more momentum it has. Cool. Is that similar to kinetic energy? Yeah, it's kind of the same concept, right? Except that momentum is used to define things differently. That's why they're different equations, right? Even though you're discussing the same base concept, the way something moves, momentum is used to answer different questions, essentially. If I don't care about the quantifiable energy of a system, I just care about what it's doing, then telling me kinetic energy is kind of making the question harder, in essence. This can also get, of course, much more complicated at this very simple level, though. There you go. That's momentum. So why in rugby is momentum important? Why are they all big, muscular men? Because they're very large and they can move very fast, right? If we go to American football, right, your defensive line, for example, it doesn't need to move very fast. They just need to be really big. So what are we talking about here? Well, let's do an example. Again, are these going to be super simple? Yes, but I'm still going to run through various examples for you. Calculating momentum of a football player in a football. So if I get a 110 kilogram football player and 8 meters per second, what is his momentum? Well, momentum is mass times velocity. So 110 kilogram person moving 8 meters per second gives me 880 kilogram meters per second of momentum. And a kilogram meter per second is the SI unit of momentum. Again, kinetic energy was Newton's. So momentum technically doesn't have like its own SI unit. It just mashes together mass and velocity. Compare that momentum to the momentum of the football. If it's, say, thrown at 25 meters per second, but the football only has 0.41 kilograms of mass. Well, easy enough. Multiply 0.41 times 25, we get 10.3 kilogram meters per second. So a player that is a lot larger, but moving a lot slower, has 85.9 times the momentum of the football. And that makes sense because the football needs to be moving stupidly fast to make up that difference, right? These are, as I said before, all very things you already know, right? If you throw a football at a dude, the football isn't really going to stop the dude because the dude is really big. And now you have the math to prove it. Congratulations. So what am I looking at here? This is the actual force versus the effective force. Or actually, I'll go over here for the better explanation of what I'm discussing. Yeah, there you are. There we go. So the effective force versus the actual force describes the force over a very specific amount of time. So why is that important? Because your total force that you put into something is dictated. The total force you put into something is not purely dictated by the amount of force you do, but also by the amount of time you're doing the force. Doing is like a really fun physics word. It does a whole lot of work for you, funny enough. This is why, for example, balls are elastic. A football is not a super hard object, not because it would break toes. You can just put something hard around the toe to prevent it, but it also allows force to be impacted more into what you're dealing with here. The longer you apply a force, the more forces applied to the object, right? And the way to describe how long you apply a force to something is what's known as an impulse, right here. The net force times delta t equals delta p, which is, again, momentum. And the change in momentum is your impulse. So the more momentum that you impart into something, the larger the impulse, and the larger the momentum, the bigger change in what you're changing, usually velocity in that point. This is why you have follow through, for example, right? When you swing a baseball bat, you don't stop the baseball bat as soon as you make contact with the baseball. You follow through because the continuing contact made by that baseball, even if it's fractions of a second of that baseball to that bat, continues to add force, continues to increase the impulse, and therefore increase the momentum to the baseball, allowing it to leave the batter and go for that home run even further away. That is impulse. It is, as I said before, duly connected. It's something we all know already. You're taught to follow through when you connect with something, right? Your golf swing, golfers look ridiculous. Well, sorry, I take that back. Golfers don't look ridiculous, but it's very interesting that a proper golf swing has you going all the way over and adjusting your body, adjusting your feet, even though the thing you're touching is on the ground, right? You pull back a whole bunch and you swing forward a whole bunch. You're making essentially almost an entire arc with a golf club to successfully swing it and hit the ball. You're focusing not exclusively on connecting with the ball, but you're focusing on the entire process. And the connecting with the ball side of it is arguably less important than the entire swing itself. And this is true for, again, any sport that involves a stick and a ball, right? The accuracy of the swing is something you have to just be secondary to the overall motion. Golfers don't have to worry about hitting the ball because they understand the more important aspect of it is the impulse being applied to the golf ball than their accuracy. They can train themselves to be accurate and then focus on the important things, which is the application of their force. Real big, complicated explanation for impulse, but I hope that makes sense. And the equation shown here, delta P equals F net delta T, is that process. Or this triangle here is your impulse, is what you're actually doing to your total force, which is the blue line shown here. 8.3 will be an example of this conversation. Again, this is pretty simple math, as you'll come to see. So here we have an example of billiard balls. That's pool balls, by the way. So two identical billiard balls strike a rigid wall at the same speed and are reflected without any change of speed. So imaginary frictionless physics, right? The first ball strikes perpendicular to the wall. The second ball strikes the wall at an angle of 30 degrees from the perpendicular and bounces, again, 30 degrees off. So determine the direction of the force of the wall due to each ball, and they calculate the magnitude of impulses of the two balls in the wall. So how do we do this? Well, to solve the first one, we need to first determine the force on the wall, and then consider the force of the ball due to said wall there. Well, how do we figure that out? Well, let's take a thought about Newton's second and third laws of motion here. What is Newton's second law of motion? F equals ma. What is Newton's third law of motion? Equal and opposite forces, right? So, since the first ball is shot perpendicular to the wall, so it essentially strikes the wall directly and comes back, all force put into that first ball is coming right back at you, or positive x and negative x is the directions. However, the second ball continues with that momentum but has a y directional component to it. Since it's striking at a 30-degree angle, whatever is coming off is also going to have an x and a y component. However, they're still going to be proportional because we have this magical no reduction in speed from the billiard ball striking. So it doesn't matter for the math if you're at an angle or not. Your total forces front and back are going to follow, and your total impulse you put at the beginning is going to be your impulse that you take out at the end, which is exactly what's shown here when we go and calculate the impulse of the ball. So since our x component is the mass times whatever force we put into it, our final x component out is just going to be the opposite of whatever we put in. If the force going into the wall is, name the number, the force coming off of this wall is same number. Again, this is in pool. This is why it's important to consider how hard you strike the ball. Expert pool players aren't going 100% with every single stroke of the cue, right? Soft touch is important to land the cue ball where you need to make your following shots. And when you're doing bouncing off the rail and stuff like that, a good pool table, you should assume, gives you a repeatable outcome. Or if I hit this side of the pool table at 30 degrees, it's going to bounce off at 30 degrees. And if I put a medium amount of force into the rail, into the side of the pool table, I'm going to get a medium amount of force out of the side of the pool table. That's allows pool to exist. And that's why it's so popular, because you can get good. You can train your body. Same thing, stick and ball, right? You can train your body to be able to answer all of these physics questions without having to like calculate this physics out ahead of time. But funny enough, when you calculate it out, the math matches the realistic outcomes. Part of the labs we've been doing is a lot of guess how something's going to happen and then record yourself doing it and find out your answer is correct, right? And as long as you're not like, you allow for drag and friction, stuff like that, to have the actual number be off a little bit, a lot of your numbers have been very accurate for a reason. Because this math works. Newton's laws of motions at a macro level are very accurate, even though they're 500 years old. So again, you can go back. This question here is more just kind of showing you that the math is the same one side or the other. That's why I don't give you any numbers, but cool. So that was impulse. So let's move on. And it's conservation of momentum. This is something we talked about already with energy and momentum and energy. As I said, that's in 8.1, kind of the same thing. They're basically the same equation, right? MV for momentum, 1/2 MV squared for energy. So any energy you conserved is also by definition momentum conserved. In the real world, however, friction, drag, stuff like that remove some of the energy, therefore remove some of the momentum. But at a macro level, when these two cars run into each other, the harder the M1, the faster M1 is, the larger M1 is, proportionally M2's getting more damage. So yeah, your total in is equal to your total out, stuff like that. we say isolated system because that just kind of makes the math easier. If you do not have an isolated system, other things are inputting momentum and inputting energy, makes your math equation longer, but you're still doing the same basic concepts and the same basic principles. Cool. Let's go on to collisions now. So conservation of momentum, as I said before, says that both sides of the equation need to equal out because you can't lose energy without accounting for it, and therefore you can't lose momentum without accounting for it. So when we look at examples like this, or this, when people calculate, say, pre SpaceX, you'd shoot a rocket up in the air and it'd be sectioned, right? Have chambers to it, and then as the big rocket, for example, the Saturn V, right, the gigantic rocket, the big rocket would run out of fuel, escaping Earth's gravity, and then it would separate, and that separation would allow smaller rockets to go into space and, say, take someone to the moon. And that separation, in fact, had to be specifically calculated because the amount pushed out and the amount pushed back, you need to care about weight, you need to care about velocity, stuff like that. If you push, if you separate too hard and you throw off the trajectory of your payload rocket, well, that's kind of hard to get to the moon, right? So you need to remember they both have the same momentum, but the momentum's impact on velocity is dependent on the mass. Cool. So a whole bunch of stuff. Let's pare it down a bit and let's talk about various types of collisions. Here you can see on the side here, 8.4 and 5 is 1 dimension, 8.6 is 2 dimensions. We just break down XY components. We did that already in like chapter 2 and chapter 3. So keep track of your math as you do this stuff and you'll be fine. So what does a one-dimensional collision look like? Here we're going to, unless I say otherwise, assume frictionless, assume dragless, all that, of course, right? One elastic collisions are where things bounce off of each other. Inelastic collisions are where things don't bounce off of each other. So pool balls, for example, are elastic, right? Because when they strike each other, they bounce off and go their separate ways. A car accident would be inelastic because when one car smashes another car, they kind of become one mass afterwards. That's the classic way to define those two. However, all momentum either party had at the start needs to total into the new momentum at the end, which is what's shown here in these example equations. You know, momentum P1 plus P2 is equal to your new momentum. So your total change in force is 0, total change in energy is 0. I am re-going over concepts from chapter 7. Right. So here we have down here, 8.35 is simply the energy version of the momentum equation, which is 8.34. 8.34 is momentum, 8.35 is energy. As long as what you start with and what you end with is the same, you're set. So let's do, I think 8.4 is my example I chose. Let me check. 8.5 is the example I chose. Okay, cool. I guess I'll also go here. Take a look at these before and afters. We notice that if M1 and M2 are moving and they have a mass and a velocity in M1 V1, M2 V2, they therefore have a momentum. So I can calculate the total momentum of this system here by figuring out the masses and the velocities, right? So I have a total momentum at the start. And then, for example, down here, let's say they bounce off of each other. And then I can figure out, I can use that total momentum to calculate the momentums afterwards. If they're both moving and they're still separate, they still have separate masses haven't changed, but velocities have. Even if I have a negative velocity, such as V1 prime here on the left, once I do all my math, I just need to make sure the numbers equal out. Your initial and your final need to be the same totals. Let's go over 8.5 as an example of that. I think that's in the next chapter. Yes, it is. Good. The inelastic collision example. So the big difference between elastic and inelastic collision comes in the form of what is shown here. where inelastic means your mass is changed. So instead of having an M1 and M2 for P1 and P2, you now have a final, which is M1 plus M2 for this example shown here, or 2M actually in this example shown here. Let's go over this hockey puck example as an to expand on this concept. So for question A, can you find the recoil velocity of a 70-kilogram ice hockey goalie who was originally at rest, so velocity of 0, but catches a 0.15-kilogram hockey puck that was slapped at him at a velocity of 35 meters per second? So you have a M1 V1. You can figure out a momentum for him initially. You can figure out a momentum for the puck initially. And then you figure out the final momentum of him. Given that he catches the puck, meaning that him and the puck are essentially the same system. And then B, how much kinetic energy is lost during said collision? Assume friction between the ice and the puck is negligible. So we're in magical physics land where we don't really care about the extra stuff. So how do we figure this out? Well, if I can figure out my initial momentums, I can figure out my known final momentums, I can calculate for things I do not know, right? So my initial momentum has an M1 V1 and M2 V2 for the hockey player and the puck. In this case, the puck is M1 and the goalie is M2. So the puck's velocity, V1, is given by 35 meters per second, and the V2 of the goalie is 0 because he was stationary. But the final, or in this case, the primed, masses and velocity are different because I don't have separate masses and velocities as shown in 8.46. He's holding the puck, so his mass and the puck's mass need to be combined into one new thing, which is what 8.47 is telling us. So I can figure out 8.47. I can add these two together to get a mass of the total system, and therefore solve what I need to solve for. Cool. Let's do that, right? So I know that my V2 is 0 because the guy isn't moving, right? Anything times 0, 0. So I can cross out M2 V2 from equation 8.46. And since the total system of the hockey player with the hockey puck has one mass, it therefore only has one velocity to calculate, which is why I just have a V prime down at 8.47. There is no V1 prime and V2 prime. So this equation here yields all the relevant information. I need to know the mass and velocity of the puck, essentially, because I need to know the momentum of the puck, P1. Momentum of the goalie is 0 because he's not moving. And the final momentum is given by the mass of the two times the unknown third velocity. So when I plug all this information in, I get a total velocity of the goalie with the puck of 7.48 times 10 to the negative second meters per second. Super duper slow, right? Or hockey goalies don't move a lot when they catch pucks, which is a good thing for hockey goalies, right? So what is my kinetic energy transfer? Well, this recoil velocity is small in the same direction as puck's initial velocity, as we might expect, right? So before the collision, we did have a total kinetic energy only of the puck because the goalie's kinetic energy was 0, right? Because he's not moving. We have a kinetic energy of the puck of 91.9 joules. And then after the collision, we have an internal kinetic energy, again, of the mass of the two times V squared on new velocity. It's real small, of 0.196 joules. So a little bit of kinetic energy since this large hockey player is moving tiny amount. So internal kinetic energy essentially of 91.7 joules in the direction of the hockey player going backwards. So the puck lost 91 joules of energy by being caught. Where did it go? Well, it went into the heat of the pads, the slapping sound of him catching it, stuff like that, right? That is inelastic collisions. The difference between elastic collisions and inelastic collisions is if you need to change 8.46 to 8.47. Those two equations are the entire game. We can do this in two directions. Again, the only thing we need to change is we need to, instead of just running the numbers straight, take into account x and y variables by using our trigonometry. I've went over this a whole lot already. So again, I'm skipping over some of the super basics of the conversation because I'm assuming at this point you've done so many sine of theta, cosine of theta conversations that you know how to do it, right? Right, draw triangles, right? Understand where the stuff is coming from. And again, there you go. For conservation of along the x-axis, you use the cosines, and for along the y-axis, you use sines. It's always useful to draw these things out and figure out your SOHCAHTOA to make sure sine and cosine is correct. That way you also have an understanding of how to orient things along your coordinate system of choice. If you go into a different coordinate system, right, these things would be different. But in general, I'm not trying to trick you here. You can just say x is cosine, y is sine as well. But draw it out. Please draw it out. I like that. Let's go over 8.7, and then we're pretty close to being done, actually. Very short chapter on my end. Determining the final velocity of an unseen object from the scattering of another object. Again, this goes into the actual like science that people do here. Suppose the following experiment occurred. A quarter kilogram object, M1, is slid on a frictionless surface in a dark room, where it strikes an initially stationary object with a mass of 0.4 of a kilogram, M2. The quarter kilogram object, M1, emerges from the room at a 45-degree angle with its incoming direction. The speed of the quarter kilogram object was originally 2 meters per second and is instead 1.5 after the collision. Calculate the magnitude and direction of the velocity of the second object. So you put something into a box that you can't see, and it comes out at a different angle. What was the original thing doing? Sorry, what was the thing that struck doing to cause that change? Because you don't know what happens in the box. You simply know how it exits. You know how it enters. You know how it exits. You know how big the thing in the box is. So what is the thing in the box doing to cause that particular outcome? Or can we figure out momentums, right? And here also it tells you that object 2 has a magnitude in the direction of velocity. So it's probably moving, which means this is an elastic collision. Elastic collision means, right, your initial momentum P1 plus your initial momentum P2 equals your final momentum P1 plus your final momentum P2. So let's write out equations and see what we can solve for. So we can know that M1 V1 can be broken down into its x and its y's, with M1 V1 prime cosine and M2 V2 prime cosine for x's, and then sine for y's, right? So if we take all that stuff out there, we can start to rearrange our equations a bit to make them a little easier. Again, the textbooks like to kind of skip ahead in trigonometry and hope that you remember that if you write the equations out, you can then reconstruct them in certain ways, which is why it jumps straight to tangent, given that tangent is sine over cosine. And it's knowing what we're trying to solve for, which is V2, V prime 2, and theta 2. You're not going to have to do this necessarily at the beginning. My suggestion to you is, if you look at this, you're like, tangent of theta 2, what's that all about? Write out your equation showing up here at the top and plug that into your overall concept of initial momentum. Sum of initial momentums equals sum of final momentums, and try to reconstruct why they're doing a tangent of theta 2 here. When you do that, you're going to see how solving the equation before you plug in the variables will save you time and paper and confusion of having to track all your variables down here. So when you solve for the theta 2 or the theta of the object that is unknown, we learn that it's about 312 degrees. So given the masses of the two objects, if the mass of object 1, the quarter kilogram object here, 250-gram object, I'll say, goes in straight and comes out at a 45-degree angle, that's a 135-degree shift in its direction. Its object emerges from the room at angle 45 from its incoming direction. Yeah, there we go. It's a 135-degree shift here, right? That's a big shift. So that is happening if object 2 is coming in at a 312-degree angle from where it's coming from. So 312 is down here in quadrant 4, right? Given that information, we can then figure out the velocity of the object after the collision to figure out where it's going. In that case, so once I know the theta of the object of the second object, I can simply again plug it into my main equation here, solve out for v2 prime instead of theta 2, and it's pretty simple math. Again, if you, I keep saying again, it's just a habit of mine. If you look at 8.71 and like, where did this equation come from? I don't remember seeing it in the book. 8.71 comes from this big long equation here, and it comes from some of your initial momentums equals some of your final momentums, conservation momentum. If this is confusing to you, write it out long form and just work your way down. This stuff is best done by doing. But the math itself is not super difficult. It's just moving the pieces and the parts around until you get what you need to solve for. In this case, we find out that the object 2 is leaving at almost a meter per second, which is slightly, is about what, a third less than object 1's leaving velocity. And of course, that makes sense too, right? Because object 2 is 400 grams, object 1 is 250 grams. So it's not going to be moving as fast. I hope that made sense, right? The book intentionally did not go through the long form math of it, because the long form math is a bunch of examples of moving pieces around until you get the equation you want. And the moving the pieces around is basic algebra. So if you're confused by it, again, my suggestion, write it down and just do one step at a time, right? You're going to get good at reconstructing math equations by reconstructing math equations. And that actually it's basically the conversation. The last chapter is about rocket propulsion, and it's a equation relating gravity to the masses of what we're talking about here. Is essentially, as your rocket fuel runs lower, how's that affecting where you're going? And it's also how is it affecting how fast you're going. It's more of just a cool thing to discuss here. I don't think I really asked many questions in the text about it. And it's just momentum stuff, right? How much energy is being expelled from the rocket is dictated by how much energy is being used by the rocket's fuel burn rate and stuff like that. It's all fun stuff, but the math is, again, not super relevant in this class. Delta M does infer some calculus. Is shown here. It skips the calculus and just gives you natural log information. But yeah, I don't think it was super relevant to what we're discussing here. So that is the conversation. That is linear momentum and collisions. Again, the base takeaway from this entire conversation is the equation of momentum is super simple. Mass times velocity. How much you do that over time gives you impulse, which is the application of momentum. And all momentum you start with in a system needs to also end up with the same, barring real world zapping of energy, heat, friction, stuff like that, which you, if I ask you to take into account of, you do. The equations can get pretty messy, as the last example shown, but they're messy in a manageable way if you take proper notes and give yourself room to solve the problems. So that all being said, thank you for watching the lecture. I hope you enjoyed it, and take care.